10A, Static Electricity and Electric Fields. 10.1. Introduction. As stated repeatedly in this textbook, God created us to manage His world, Genesis 1:28. He has hidden many useful resources in His creation. Much of our dominion work is discovering and using these resources efficiently and safely. In doing so, we learn more about God's glory as well as our own. As Proverbs 25:2 states, "It is the glory of God to conceal a thing, but the honor of kings is to search out matter." God shows His greatness by hiding from us many of the marvels of His creation. We come to enjoy the glory of being human by finding what has been hidden and using it to benefit ourselves and others. There is a form of energy that God has hidden throughout the universe for His glory and for our benefit. This energy, electrical energy, is all around us and is even essential to the proper functioning of our bodies, but only relatively recently in history have we been able to make good use of it. How can you tap into this valuable resource? Believe it or not, you can begin by reaching for the comb in your pocket or purse. Try this experiment. Tear off a few small bits of paper and put them on the table. Run your comb through your hair and then hold it over the bits of paper. They will jump up and stick to the comb. Why do they do that? The answer is static electricity. The study of this type of electricity deals with stationary electrical charges and the forces that they exert. 10.2. The electrostatic force. People have observed static electricity throughout history. The most dramatic form has always been lightning discharge. But over 2,000 years ago, the Greeks observed that a piece of amber they had stroked with wool or fur could magically attract certain lightweight objects. Chapter 5 explains that the force between electrical charges, or the electrostatic force, is much stronger than the force of gravity. As the bits of paper in our experiment sit on the table, gravity pulls them down. The electrostatic force from the comb is able to overcome gravity and pick them up. How does the comb acquire this force in the first place? To answer this question, we must first examine the source of electrostatic attraction. 10.3. Electrical charge. When electrical charges were first investigated in the early 1600s, scientists soon discovered that electrically charged objects could exert forces of both attraction and repulsion. These two effects suggested that there must be two kinds of charge. This reasoning was based on experiments similar to the following, which you can recreate yourself. Hang a rubber rod by a string. Rub one end vigorously with a wool cloth or a piece of fur. This will give the rod one kind of charge. Hold another rubber rod in your hand and rub it with the same cloth so that the two rods will have the same charge. Bring this rod near the tip of the hanging one, but do not let them touch. Your rod should repel or push away the hanging rod. Now hold a glass rod in your hand and rub it with a silk cloth. This rod will also acquire a charge. Bring the glass rod near the hanging rubber rod. It should attract or pull the rubber rod. This effect is the opposite of what occurred with the like charges. Next, hang a glass rod by the string, rub it with silk to charge it. Repeat the experiment. First using a glass rod rubbed with silk, then a rubber rod rubbed with wool or fur. The results are listed in Table 10-1. The law of charges summarizes the table. Like charges repel, unlike charges attract. After extensive experimentation, physicists never found a charge that repels or attracts both rubber and glass rods. They concluded that there are only two kinds of electrical charges. We have Benjamin Franklin to thank for the names of these two kinds of charges, negative and positive. We need to examine matter at the particle level to understand the source of electrical charge in objects. Chapter 2 describes the structure of atoms. They are made up of three important particles: protons, neutrons, and electrons. Protons, which each carry a single positive charge, are fixed in the atom's nucleus, so they cannot move freely through matter. Neutrons, which are neutral and do not contribute to electrical charge, are also in the nucleus. Electrons, which each carry a single negative charge, are found within the atom, around its nucleus. The outermost electrons that form chemical bonds are easily shared, gained, or lost. It is these mobile electrons that account for the movement and storage of electrical charge. Normally, most objects have an equal number of electrons and protons. The opposite charges of these particles balance each other so that there is no detectable electrical charge on the object. Such objects are said to be neutrally charged. Sometimes, though, especially on low humidity days, you receive a crackling shock when taking off your favorite wool sweater or when you reach for a metal doorknob. Where did that electricity come from? In some materials that have a weak affinity for electrons, the outer, loosely held electrons of their atoms are easily removed through friction, such as simple rubbing. When you walk across a carpeted floor, your shoes pick up electrons and you become charged. When you touch a doorknob, the charge difference between you and the knob results in a shock. When we rub two objects together, often one object loses electrons and the other gains them. The object that loses electrons has fewer electrons than protons, and so has a net positive charge. The other object, which gained electrons, has more electrons than protons, and so has a net negative charge. The net positive or negative charge is measured in coulombs. The coulomb C is the SI unit for electrical charge. 1 coulomb is the charge carried by approximately 6.24 times 10 to the power of 18 electrons or protons. Chapter 9 discusses how thermal insulators have tightly held electrons and how thermal conductors have loosely held, highly mobile electrons. In a similar way, electrical insulators, such as wool and glass, are much more effective at storing charges because electrons can't easily move toward or away from charged areas. Electrical conductors, such as metals, do not easily store charges unless they're totally surrounded by an insulator. 10.4 Electric fields. The electrostatic force is a field force. That is, a charged object can exert a force on distant charges, not in direct contact with it. An electric field can be described accurately only with mathematics, but physicists model these fields using lines of force radiating outward from a charged object. Lines of force are also directional. They align with the direction that the electrostatic force vector would move a tiny positive charge, called a test charge. If the source of an electric field is a strong positive charge, then the lines of force point away from the source because, like charges, repel. On the other hand, if the source of an electric field is a strong negative charge, then the lines of force point toward the source because opposite charges attract. Keep in mind that Figure 10-7 shows two-dimensional models of three-dimensional fields that surround the charges and that any neighboring charges are assumed to be too distant or too weak to noticeably affect the fields. Lines of force in the field model are useful because they help us visualize both the direction and strength of an electric field. The field strength is represented by the distance between the lines of force. Near to the source charge, the lines are very close together, indicating that the field force is strong. The lines spread apart farther away from the source, showing that the field weakens with distance from the source. Since each electrical charge exerts a field, electric fields interact when electrical charges are brought near one another. The electric fields between opposite charges bend toward one another in attraction. The electric fields between like charges bend away from one another in repulsion. Field lines cannot cross each other. If they could, the electric field vector at the location where the lines cross could point in more than one direction, which is impossible. The electric field vector can point in only one direction. The field model is important for understanding many properties of matter, such as electrical and magnetic induction. We will discuss electrical induction in the next subsection and magnetic induction in Chapter 11. 10.5 Electrical Induction. Recall the comb and paper experiment at the beginning of this chapter. Why did the comb attract the bits of paper? The comb became charged as you ran it through your hair. The bits of paper, on the other hand, were probably not charged. They were attracted to the comb, but not because of the attraction between two electric fields. There is another way that charged objects can exert the force of electrostatic attraction. Electrical induction is the creation of a charged region on a neutral object when exposed to a strong electrical field. As the comb approaches the bits of paper, it produces a temporary area of opposite charge on the part of the paper nearest the comb, Remember that the paper contains equal numbers of protons and electrons since it is neutral. The charged comb, which was initially neutral, now has an excess of electrons, which have been removed from your hair. The electric field created by the net negative charge in the comb repels electrons in the bits of paper. Since paper is an insulator, it is extremely difficult to remove electrons from the paper fibers. Instead, the electrons in each molecule rearrange so that the molecule becomes an electrical dipolar-neutral molecule, whose electrons have shifted to form positive and negative ends, or poles. All the molecule's positive poles point toward the negatively charged comb, and its negative ends point in the opposite direction. The result is that the interior dipoles neutralize each other as negative poles attract neighboring positive poles. But the paper's surface has a positive and a negative region. See Figure 1010. This positive region on the bits of paper is attracted to the negatively charged comb as if the paper had a net positive charge. Water molecules are naturally dipoles. You can demonstrate this using a balloon and a water faucet. Charge the balloon by rubbing it with a cloth, preferably wool. What kind of charge should it have? Turn on the faucet so that a narrow, smooth stream of water flows out. Bring the balloon near this stream without touching the water. The charged balloon will attract the water molecules and cause the stream to bend. See Figure 1012. Water molecules play an important role in how objects lose their charge as well. In the comb experiment, the comb's charge will leak away or electrically discharge, even if you don't touch it, because of water molecules in the air. For this reason, all the demonstrations in this chapter work best in low humidity weather.